All right, homework 5, part 2. We are going to, for a turbine generating power from a flowing fluid, use momentum and kinetic energy balances to show that the maximum power generation is assuming perfect efficiency, that the difference in the kinetic energy of the inlet over the outlet flow is converted entirely to useful work, occurs when the ratio of the outlet to inlet velocity is 1/3, which is Betz's law. So here's a picture of our turbine generating power from a flowing fluid. We have a fluid coming in, a fluid going out with a turbine in the middle. So rho times the area of the turbine times the velocity of the fluid is going to be equal to the mass flow rate inside the turbine. We also have a velocity coming in times the area of the pipe times rho, which is also equal to the mass flow rate going in. And for the outset here, the velocity going out times the area going out, this area on the outer diameter of our generator here, times rho again is going to be equal to the mass flow rate going out. And so we have perfect efficiency here, so that we know that the mass flow rate is equal to the mass flow rate going in is equal to the mass flow rate going out. So let's look at our momentum balance. The derivative of the momentum times the velocity of the system over time is going to, with respect to time, is going to be equal to velocity going in times the mass flow rate going in minus velocity going out times the mass flow rate going out plus the force. We can rewrite this, and knowing that the force is negative. The force is negative because if the force was positive, it would be the turbine acting on the air, but we want the air to be acting on the turbine. Is equal to V1 minus V2 times the mass flow rate. However, we already said that the mass flow rate is equal to rho SV right here. So we can trade this guy for rho SV. Very good. Now let's look at a kinetic energy balance. We can re-describe our kinetic energy balance, or we can describe it in terms of power. We know that power is equal to the change in kinetic energy over the momentum. We know that kinetic energy is equal to 1/2 mv squared. So if we throw this into the equation here, we will be left with V1 squared minus V2 squared over 2 is equal to, these ends will cancel. Times the mass flow rate, rather. And that'll be rho SV. Forgot the mass flow rate part there. Perfect. Okay, next part here. We can also describe power as the negative force times the velocity. And we have the negative force equation already, so we can throw that in. So power is equal to V1 minus V2 times rho SV, and then that's going to be V squared since we have this other V term. And now that we have these two equations, we can relate these for kinetic energy balance here. So we'll be left with V1 minus V2 times rho SV squared equal to V1 squared minus V2 squared all over 2 rho SV. Alright, big cancel time. You ready? Here we go. That's gone. The square's gone. That's gone. This is going to go away. Since this is a difference of squares, we can rewrite this as V1 plus V2 times V1 minus V2. So we're getting rid of this V1 minus, then we are left with just that V plus V2 over 2. So then we are left with V is equal to V1 plus V2 over 2. That is our equation for velocity. So we can plug this equation for velocity right back on into this equation up here. We are left with V. Let's put an arrow so we know where we are. V1 squared minus V2 squared all over 4. Since we're coming in with another 2 here, just bump that to 4. And that's going to be rho s times V1 plus V2. Boom, boom, I like it. So this is power. So we're plugging into that power equation there. Now let's combine some like terms here. Rho s over 4. That is going to be V1 cubed plus V2 squared V1 squared V2 minus V2 squared V1 minus V2 cubed. Alright, so now this is where we kind of go to a more advanced step. Looking at this right now, you might be wondering how we're going to get at this ratio that we need to prove. And this is a kind of a big jump in this step here. So what we're going to do is we are going to pull out our V1 cubed here and kind of put these in terms of ratios. So this is going to be 1 plus V2 over V1 minus V2 over V1. Sorry, I already messed it up. V2 over V1 minus V2 squared over V1 squared minus V2 cubed over V1 cubed. So now that we have these in terms of ratios, we know that R is equal to out over in, and V2 is our out, which is just equal to V2 over V1. So that means this is R, and then this means this is R2, and then this means this is R3. R to the 3, R squared, R cubed. So if we take the derivative of P with respect to R and set it equal to 0, we can pull out these constants. That's a non-factor. And we are left with 1 minus 2R minus 3R squared equals 0. Now we can factor this, and we are left with 1 minus 3R and 1 plus R equal to 0. Which means we have R is equal to negative 1 and R is equal to 1/3. We don't want this because if the ratio is a negative number, that means the flow is going backwards, and that's not what we want. And here is our solution, or our proof, that the ratio of the outlet to the inlet for the flow has to be 1/3 for maximum efficiency. And then let's just go back up to the problem here. When the ratio of the outlet to the inlet is 1/3. So there we are. Very good. See you in part 3.